right, welcome to today's physics video. We're going to be learning about systems of objects. Panette, do you want to say hi again?
Hi, it's Panette.
We had to do a do-over. All right, so the learning targets here, basically we're just going to be doing Newton's laws problems again. The big difference is this time we're going to be doing Newton's laws problems that deal with what are called systems of objects, okay? So what is a system? Well, a system, the textbook definition of a system is it's just a collection of objects, all right? For us, usually either the system won't move, so the objects won't be moving, or if they are moving, they'll be moving together, okay? So a simple example would be, let's do a semi-truck. That's probably an easier example. So here's our semi-truck pulling a trailer, right? Okay, so when the semi-truck drives down the road, both the cab and the trailer move together, right? Okay, so that would be an example of a system, okay? Now, when you talk about a system of objects, there are two types of forces, all right? There are what are called external forces, which would be forces that come from outside the system. So in this example, friction from the road pushes the cab forwards, right? Force of friction pushes the cab forward, so that would be an external force. The friction is what makes all of this go, okay? Now, the reason the trailer moves is because the cab pulls it forwards. That is an internal force, right? Our system was defined to be the cab and the trailer. Friction comes from outside that system, so that's an external force. The cab pulling the trailer is an internal force because it's a force that comes from an object inside the system, okay? So, why do we care about all of this? Well, when you make your free body diagrams, the only forces that you care about when you make a free body diagram for a system are the external forces. So external forces do go in a free body diagram, and internal forces do not go on a free body diagram. All right? So that is that. Now, that distinction will, I think, be made clearer as we go through more examples. Okay, now we got to talk about one other real quick thing, which is we got to really quickly recap Newton's third law. All right, so remember, Newton's third law, anytime two objects anywhere in the universe interact, they exert equal forces on each other. If the cab pulls the trailer pulls the cab. Those forces are equal, right? So notation. So suppose I give you an example in which you've got object A pushing object B, and you've got object B pushing object A, okay? The notation we're going to use is this. The force of object A pushing object B is going to be written as the force on object B by object A, okay, which is backwards from the way that I think that I would like to write it, but that's the notation that's usually used. So the first subscript letter represents the object being pushed, all right, and the second subscript letter represents the object doing the pushing, or pulling, I guess. Okay, so Newton's third law says that the force on object B by object A is both equal and opposite to the force on object A by object B. And the speaker almost fell on my head up here. This doesn't want to stay up. All right, so we will be using this notation frequently in this section, okay? All right, so probably the easiest way to do this is to just dive in and do an example. So here we go. So the example says, two boxes sit on a horizontal frictionless surface as shown in the drawing to the right. Box A has a mass of 20 kilograms, box B is 60 kilograms. Box A is pushed to the right with a force of 240 newtons. All right, and what we're going to do is we're going to try to find two things. We're going to try to find the acceleration of the two boxes, and we're going to figure out how much force each of the two boxes exert on each other. All right, so here is the deal. So we're going to end up making three free body diagrams, all right? And those three free body diagrams are going to be for different systems. We're going to make one free body diagram for the system that includes both boxes, okay? We're also going to make a free body diagram for the system that's just box A by itself, and then another free body diagram for the system that's just box B by itself, okay? So before we do anything, let's kind of get a sense for what's happening here. So the idea is we've got these two boxes. Let me redraw it. So here's box A, here's box B, and Roy is pushing them, right? Okay, and then I'm going to make a terrible drawing here, and I'm going to label this as the force of Roy. I say that's terrible because I just drew my arrow pointing into the box instead of out of the box. Okay, so we are going to make 3 free body diagrams. All right, so I think usually what I'll recommend that you do is that you do all 3 free body diagrams first, and then go back and do your calculations. In other words, write out as much given information as you can for each of those 3 free body diagrams. For this one, though, it turns out that one of them is pretty simple. So for number 1, let's do this. Let's do the system of object A and B combined. All right, so here we go. So I'm going to draw the 2 objects. So here's A and B combined. All right, they're going to have a combined mass of 20 plus 60, so that's 80 kilograms. Okay, and what forces act on it? Well, there's going to be gravity, which you can certainly find. I'm going to skip it to save time in the video. There's a normal force, which would be big enough to cancel out that gravity. Again, I'm going to skip it to save time in the video. And then there's this force on box A provided by Roy. And the problem tells you that that is 240 newtons. Notice that's an external force because Roy is not in the system. Okay? So, in this interaction, notice A is going to push B, right? And B is going to push A, but those are both internal forces for this system here. Okay? So I think that's it. I think those are my only forces. The problem tells you that it's frictionless, so you don't need to worry about friction, so I think that's it. So the acceleration of objects A and B combined should be the net force on objects A and B combined divided by the mass of objects A and B combined. So my net force is 240 newtons. My mass is 80 kilograms. Divide it out and you get 3 meters per second squared. Okay? So what does that mean? Oh, well, all of the boxes are going to move together, right? They're all moving together as a system. So now I know that the acceleration of object A is 3 meters a second squared, and I know the acceleration of object B is also 3 meters a second squared. Okay? So, what I can do now is make some new free body diagrams. All right? So let's make a free body diagram just for box B. So here's box B. The problem told us that this had a mass of 60 kilograms, right? Okay, so think about the forces that are acting on it. Well, there's going to be a force of gravity that we can certainly calculate, but again, I'm going to skip it to save some time on the video. There's a normal force that cancels it out. All right, now, what's pushing it forwards? We know that it's going to accelerate forwards at 3 meters a second squared, right? Because the 2 boxes are sliding together. But what causes it to move? Well, look, Roy, in our drawing over here, Roy is only pushing box A. He's not touching box B, is he? Okay, so the reason that box B moves is because A pushes it. Okay, so this is the force on box B by object A. And notice, because my system here is just box B, this force from A is now an external force. Okay? But we don't know how much force that is. It's not 240 newtons because it's not the same as the force from Roy. It's like it's a different force, right? So, remember, big rule of thumb. Anytime you know the acceleration, find the net force. So the net force on box B is the mass of B times the acceleration of B. So 60 kilograms for box B. Acceleration is 3 meters a second squared. Multiply it out, you get 180 newtons. Okay? Now, my force of gravity here and my normal force cancel out, so I think this is just going to equal my net force, right? The only force acting on object B that doesn't get canceled is the force of A pushing it. So that's got to be 180 newtons, right? Okay. So that is that. So that is object B. And I think that's actually the last question we needed to ask, right? It said how much force do the boxes exert on each other? So it should be 180 newtons, right? So that should be the answer to question B. Now, the cool thing about these problems is there's a built-in check, okay? So what we haven't done yet is we haven't made a free body diagram yet for object A. So let's make a free body diagram for the system that includes just object A. All right, so if we do that, here's our drawing. The thing has a mass of 20 kilograms. So once again, we'll save some time. There's a gravity and a normal force, and the speaker falling on my head again. Screw that down. All right. So we got gravity and normal force. Those cancel each other out. There's the force on object A by Roy, which is, what did we say it was? 240 newtons, right? And that was how hard Roy was pushing box A. Okay? Now, the idea is Roy's pushing box A forward, but box B is in the way, kind of resisting its motion. So there's a backwards force on box A by box B. Okay? But remember, Newton's third law tells us that this force and this force are equal and opposite. So if the force on B by A is 180, then the force on A by B is negative 180. Okay? Because it's an action-reaction pair, right? So now, I think I can find the net force on object A, right? My gravity and my normal force cancel, so it's the force on A by Roy plus the force on A by B. So that's 240 plus negative 180, which gives me 60 newtons. So that's the net force on A. So I can find the acceleration of A by doing net force over mass. Net force is 60 newtons. Mass is 20 kilograms. Divide it, and you get 3 meters per second squared. And we're happy, because that's what we got the first time, right? Okay, so everything works out. All right, so that's how those work. Now, this one was fairly simple, because there was no friction. There are no pulleys or anything. Okay, so let's do a problem that's maybe a little bit more complicated. We'll do one with a pulley here. So I'm going to do one more example, and then I'm going to leave one for you guys to try on your own. And we'll go over it in class tomorrow, if you remind me. All right? So that is the deal. Okay, so here we go. Example number 2. So this time we've got, it's locked. So we've got this pulley up here at the top. So here's our pulley. And then hanging from the pulley, we've got 2 boxes. Box B, the problem tells us, has a mass of 6 kilograms. And box A has a mass of 4 kilograms. All right, and they're attached to this pulley. And so the idea is they're both kind of pulling down, but the heavier object is going to kind of win, right? So basically the idea is our system can either go this way if object B wins, or this way if object A wins, right? So you can probably see pretty clearly here, B is more massive, so it's going to win. But let's talk about it in terms of force. So the force of gravity on object B is going to be 6 times 9.8, so that's 58.8 newtons. Don't put a negative in, all right? We'll talk about the negatives here in just a second. All right, and over here, my force of gravity is 4 times 9.8, which is 39.2 newtons. Again, don't put in the negative. All right, I can't call those both Fg. This is the force of gravity on B, this is the force of gravity on A. So I guess the big thing I want to make sure you guys understand here is we can't make both of these forces of gravity negative, because if we did, that would imply that they were both making the system move the same way. So I guess maybe I should do that. I haven't defined my system yet. So what's my system here? Well, here my system is all of this stuff that's moving. So it's object A, object B, and the rope that attaches them. Okay? And so the idea is here my force of gravity on object B is going to pull the system this way, and the force of gravity on object A is going to pull the system this way. So what we got to do is we got to pick one of those directions to be positive and one of those directions to be negative. So since it looks like B is going to win, let's make this way positive and this way negative. So the idea is the force of gravity on B is pulling the system in a positive direction, and A is resisting that by pulling in a negative direction. Okay? So what that means then is that, let's move this over here, the net force on objects A and B combined is, well, it's the force of gravity on A plus the force of gravity on B, right? Which for us is negative 39.2 newtons plus 58.8 newtons. And I'm almost out of room, so that gives us, what, 19.6 newtons? So that's the net force on the system, all right? But so the idea is that net force isn't just moving object A, it's not just moving object B, it's moving them both, right? In kind of this weird curvy direction here, right? So our acceleration of our system is going to be net force over mass. 19.6 newtons over our combined mass of 10 kilograms. And so we get 1.96 meters a second squared, sort of in the direction of B, okay, kind of this way. Okay, that's a crappy arrow, but there you go. Okay? So that is what's happening for the system. All right, so now what we're going to do is to solve this thing, let's look at the individual masses. Okay? So let's look for a minute at just mass. It doesn't really matter which one we do. Let's look at mass A. All right, so here's mass A. It's 4 kilograms. All right, I know that the force of gravity on block A is 4 times 9.8, so that's 19.6 newtons. Now, box A, according to our problem, is going to move up, right? So let's go back to just doing up is positive, down is negative. Okay, what's pulling it up is the tension from the rope. Now notice, I didn't need to worry about the tension from the rope before because our system originally included the rope, so it was an internal force, but it isn't anymore. Okay, but what I know is object A is going to move up with an acceleration of 1.96 newtons. Writing that makes me realize that I made this force of gravity wrong. This force of gravity should have been 39.2. Sorry about that. And it should be negative. In fact, let's edit this and I'll go redo that. All right, so let's look at object A. Object A is a mass of 4 kilograms, right? And what are the things we know? Well, we know gravity is pulling it down with a force of 39.2 newtons. And we know that the tension from the rope is pulling it up, right? Because if we look back at our drawing, we know that our system is pulled up this way, right? Because B pulls down, which pulls A up. We had already figured out the acceleration, right? So we know that our system, or our object A rather, is going to accelerate up at 1.96 meters a second squared, all right? So let's do this. Let's revert back to our usual sign convention. Let's make this way negative and this way positive. So this force of gravity is negative. That means my tension force is going to be positive. My acceleration is positive. Oh, I know my acceleration. I should find my net force. So that's mass times acceleration. So this thing had a mass of 4 kilograms. Acceleration is 1.96 newtons. No, it isn't. It's 1.96 meters a second squared. So multiply this and you get 7.84 newtons. So now I ought to be able to find my tension. Net force is tension plus gravity. So my net force, we just found it, 7.84. That's going to equal the tension plus negative 39.2. So your tension force ends up being 47.04 newtons. That's the force that pulls mass A up to prevent it from falling, right? So mass A is going to accelerate upwards because the tension force is winning. Okay? All right, so finally, let's make a free body diagram for object B. All right, so for object B, it's basically the same process. You just got to watch your signs. So here's object B. It had a mass of 6 kilograms. Force of gravity on it is 58.8 newtons. This one's going to accelerate this way, right? So again, let's make up positive and down negative for this object, okay? So that means this force of gravity is negative. My acceleration is negative 1.96 meters a second squared, right? Because it's going to accelerate downwards because it's winning. But tension is going to slow how quickly it falls. So we know the acceleration. Let's find our net force by doing mass times acceleration. So that gives you 11.76 newtons. Net force is tension plus gravity. Our net force is, oh, I forgot my negative. Negative 11.76. Tension, we don't know. Gravity is negative 58.8. Do your algebra, add the 58.8, and you get 47.04 newtons again. Okay? And so the idea is this tension force equals this tension force because A and B are both pulling each other through the rope with equal and opposite forces by Newton's third law. Okay? So